Okay, so here we are again, and it turns out this is the ESS. Does anybody not understand why? It's okay. It would seem like they'd be both better off if they would cooperate, right? Cooperate. The trouble is that more than anything, the individual has to protect themselves against the worst outcome. So even if they both, you say, okay, let's both cooperate, we'll only do a year in jail. It'll be, won't be maximum security. It'll be kind of like a golf course sort of jail, right? If they did that, that'd be pretty cool. They also would still remain friends, and one wouldn't try to kill the other one when he got out of jail. But the individual, more than anything, wants to protect himself. And so, even though this is the third best outcome, it's the ESS. Nothing can beat this strategy. Okay? If one cooperates and the other one testifies, the payouts are 0 and 5 years in jail. That's the worst outcome and the best outcome. The next one, cooperate, that's great, but you can't enforce it. If you could enforce it, that would be a pretty good deal. So, even though that's the third best outcome, that's the only stable strategy there. It cannot be beat. You either play that strategy both ways, both guys do it, or one does it and the other one cooperates and he's a dead duck, right? Okay. It'll probably be something like this on the test, by the way. Okay? Just so you know. So I want you to understand why the evolutionary stable strategy is the fact for both of them. And the last time I went over this, I said this is just a one-time play. So they only play it once. And in fact, if you think about it, and you go back in time to early human prehistory, before there was written history, you don't even need jailers. You want to think about two different people who are strangers with each other. Okay? So, what's the best approach you should take with that other individual? Are you just going to say, hey, let's have a good time, we'll cooperate? Right? Now, in the Bible, there's a story where, I forget who it was, but it was, the Israelis, well, they're ancient Israelis, right? And they went over to the next village and they said, let's all have a big, feast and we'll all be friends and everything. And the other guy said yes, and the Jews went over there and they killed everybody. Okay? It was all a farce. In other words, that's the worst outcome. So the best outcome, of course, is that the ones who deceived, they're the ones that won. The other ones lost everything. I mean, it was even according to God, they had to kill everything. Not just, all the men folks in the village. They couldn't enslave the women or the children. They killed them all, even the livestock, even though the livestock would have been useful. Okay? These were sick people. I mean, you understand that, don't you? Sick. Okay, just like ISIS today. God, unbelievable. But anyway, in that case, if you're dealing with those kinds of people, you want to protect yourself. It doesn't mean that you attack them immediately. You probably probe them. and see, okay, well, let's see what I can get. Can I deceive them? Or we find out that you really can't deceive them because it looks like they're onto you too, and now it's a kind of a negotiation, right? But in general, that's the hand to play, is getting rid of the other one. Okay. Okay. The best outcome for, let's say, prisoner 1 equals, what is that? Is that's 0 years, and then, so that's the number 1 payout. The number 2 payout is where they both cooperate, CC, and they both get 1 year. And then 3, they both testify, and that's 3 years apiece. And then 4, and that's, you cooperate, the other testifies, and that's 5 years. So what's the best strategy in terms of think about the worst strategy up here. How do you avoid that? 5 years in jail.
Testify.
What?
Testify.
For both of them, right? Okay. So the ESS for this is actually number 3. Okay, so we're back to foraging, optimal foraging models here. This is an oyster catcher. We've got on kind of a Western form out here. And you can actually see mussels present and the frequency that they use them, and mussels selected and the frequency that they use them. So this is our distribution, and we see that for the most part, they select a subset of what's actually out there. Now remember, this is frequency, so even though 30 and 40 is actually right down here, that means, let's say, there's fewer individuals in that, but that's the optimal range, probably because there's cost. What's the cost in terms of this? Generally. What do you think? What's the cost for dealing with these mussels? Let's say it's not an oyster catcher, it's you. Which mussel would you want? You ever eaten mussels? No. Oh, they're good. Cozy, Italian. They're delicious. Okay, now, what would you go after?
The biggest one.
Huh?
The biggest one.
You would go off the biggest one, right. But let's say the biggest one is really, you don't actually have a hammer. You actually have maybe a stone, and the biggest one, you're going to have to pound on it for a while. But, so that's a cost. And at the same time, you get a big payoff with the biggest one, right? So in this case, you've got the subset are the ones that are kind of medium large. You get a pretty good payoff, and you're able to crack those without too much time spent doing it. Handling time is what it's called, right? So the benefit in this case is the optimal foraging model. This is what we should actually see. We would predict this. And you could turn this into an ESS as well. In fact, this is what your ESS would look like. Okay. So here we have, let's see. Model A and Model B. Now, if there was really no cost, we would love to have Model A, but it's not that. It's actually Model B. This is exactly what we see here, right? Up around this point, we have the highest profitability, because what it is doing here is it's factoring in the cost as well. And once you get to a really large size, the cost is prohibitive. So this is an example here of a mixed ESS. What's the two strategies? What do you think? Back to you, yeah. So what's the two strategies? What does it say up there? Okay. Two strategies, right? Now, could you have a strategy where everybody is robbing? Huh?
Somebody's got to be fishing, which is going to rob.
Yeah. So if everybody was robbing, there'd be nothing to rob, right? Okay, so we know that in terms of the best strategy, robbing might be good. In fact, robbing will be better if there's more people fishing. This is a classic negative frequency dependent selection. If there are more robbers around, it's better to fish. So this mixed ESS depends on what others are doing in the model. That's what game theory is all about. Now you can have much more complex games than this, obviously. But for what we're going to do now, I just want you to understand that now, if we set this up, individuals don't actually decide, oh, I'll play robber this time, or I'll play fisher. No. You're born one or the other. That's why evolutionary stable strategy. So a fisher is a phenotype, and a robber is a phenotype. The robber phenotype at certain frequencies is going to be with higher fitness, because you don't have to go fishing, which is probably costs a little bit more. At the same time, fisher is the same way. So these are phenotypes. Now, there are other models where you can actually have individuals who decide, depending on the circumstances, what they're presented with, what do I play? Do I play, let's say, a hawk-dove sort of thing? You could, under certain circumstances, even though you're a nice big hawk, and there's another hawk, but he's even bigger than you, it'd be better for you to play dove. Okay? Now, because it turns out two hawks going against each other is the worst that can happen. They can actually kill each other. Okay? Versus the dove strategy, it's actually not, you lose, but it's not a total loss, as it turns out. But in this case, these are just phenotypes. That's all they are. Okay, so this is all what I've been talking about. Oh yeah, I did mention earlier about the prisoner's dilemma that there's another strategy that you play over and over and over again. In other words, you can actually, you know how your partner, what kind of reputation they have. And that's called tit for tat. So, just so you know. Okay. So I might actually set up a situation on the test, let's say. I haven't put a question on that quite like this, but it'd be simple. I'll say, you know, here's a situation. What kind of strategy is this? it could just be one ESS, or it could be a mixed ESS. It's up to you to decide. And then I'd ask you, well, why? And how is it that if it's a mixed ESS, then why is that? Why are both strategies actually optimal depending on what others are doing around you, right? Now we're going to be doing something very much like this. It's called the Huck versus Dove strategy. And this is going to be on an Excel spreadsheet. We'll do it, I don't know, maybe next week, we'll see. In that case, there's going to be some mixture. So obviously, you could have all hawks. You could even have all doves. But usually there's a mixture in terms of frequencies of both, depending on the frequency of the other one. And if you actually look at, we'll look at the payoff structure, you can see what it's actually like. It's a little bit more involved than what we saw with the prisoner's dilemma. Here's some male crickets called to attract a female and face a risk of being parasitized or killed by some wasp. Some male crickets intercept females on their way to the caller males. Okay? Now, obviously there's a cost. In fact, if everybody, in this case, if you go right to the female, what advantage do you have?
Not getting noticed.
Yeah. Now, also, if a lot of people, or a lot of crickets are actually playing the one where they make the call to the female cricket, even though they might get parasitized, what kind of an effect would that be? Think about the selfish herd, dilution effect, huh? So there's lots and lots and lots of individuals that are all playing the first strategy. They're calling, they're not intercepting. It's actually better in a lot of respects because you're reducing your chances of getting parasitized. If there's a whole bunch of you all calling, the parasitic wasp is only going to go in and get a few of you, let's say, not very many. Okay? Now, of course, the other strategy depends on if there are a lot of males, then you can also, they can get, the males that are calling, well, their females can get intercepted. So there's a couple of problems with the calling strategy. First of all, you can get eaten. And second of all, you can get intercepted if there's a lot of you. Because you're all calling, and the number of males that intercept, in fact, will be a pretty high fitness, up to a certain point. Another one, 2 hereditary forms of an African cichlid fish. In Africa, in the Great Rift Valley, there's a bunch of different lakes, Lake Tanganyika, Lake Victoria. There's these swarms of cichlids that have radiated in terms of speciation over the last 20,000 years. But this is one of the things that you often see. 2 forms. What happens is that, let's take a look at this. Okay. So here's our fish. and this other fish. And this one has a jaw that makes it's kind of asymmetrical. And so if the fish comes up on the right side of this other fish to take a bite out of him, he'll get a nice meal in terms of, let's say, mucus or scales or whatever. Okay? Now, there's also the right-jawed one, and the same thing applies. The fish in the middle, they actually get smart. Well, they either get smart or they're a phenotype where they're up on, let's say, the right jaw type of fish. And even though fish don't have shoulders, but if they did, they would look over their shoulder and know that the attack is always going to be coming from one side or the other. So the side with the higher frequency will actually have the lower fitness level, because there will be a corresponding evolutionary adaptation in terms of the host on how they'll defend against that. They'll be like always looking over their left shoulder if it's a right-jawed attack, or they'll be looking over their right shoulder. Okay. Now, this kind of actual strategy, it's been actually duplicated not just in a couple of different lakes. So, in other words, we've got a case of convergent evolution here. It's kind of like the cleaner fish stuff that we talked about earlier, in terms of a big fish coming to a cleaner station. But in this case, of course, this is completely antagonistic. Okay. And so, you would actually expect to see a graph actually like this. So, frequency of left-jawed individuals. Okay. So, in terms of in the 80s, let's say the frequency is above 0.5, right? Now, remember, if there's more of you doing that, you would expect some sort of response to the host. And we're assuming now that at a certain point, like around here, the host is actually getting the phenotype that recognizes the attack from the left side, is becoming more common, and so you get a phenotype for the host that it will recognize that sort of attack from the left side and not the other one. And so, of course, then it drives down the frequency of the left, and in this case, of course, we've got the right side, right? So this is basically kind of like a sine wave that's going on between these two species. Okay? So again, if you're rare, you have a better fitness than if you're common. But it's not always the case. And then another one that I've talked about before, the salmon that goes out to sea for 4 years, and then the jack that comes back after 2. The danger for the 4-year one is getting eaten you're out there for 4 years. And then, of course, with the jack, it's limited in terms of if there's a lot of other jacks and there's not very many hiding places near where a female is actually laying her eggs, then being a jack, you've made it back upstream, but it doesn't necessarily mean you're going to be able to father any offspring. So here's the actual hawk versus dove. And we're we're going to actually do this with an Excel payoff matrix. So if you win, you get 50 points. If you, in this case, we're setting the parameters here. If you lose, you get 0. That means you played dove. In other words, let's say you have two individuals and there's a food resource. The hawk really isn't going after the dove. The hawk is just going after, wants the food resource at the expense of the other one. So it means the loser gets 0, but he doesn't suffer a tragic cost. And then injury, that means if two hawks go at it, that's the worst that can happen to you. And if you think about it, the more individuals that play that strategy, they always battle, then the injury rate is going to go up. Okay? Now, if two losers, two doves go at it, there's a cost from actually displaying. Okay? So that's a payoff matrix. Now, when a hawk meets a hawk, we assume that on half of the occasions it wins, and on half the occasions it suffers an injury. So hawk and hawk. 1/2 50 plus 1/2 minus 100. And that, if you do that, that's minus 25. If you're a hawk versus dove, hawks always beat doves, so you're always going to get 50. Doves immediately retreat against hawks. In this case, C, so you get 0 points, but you don't get slaughtered. And then finally, when a dove meets a dove, we assume that there's always a display, and it wins on half of the occasions. So again, let's see, half of 50, it's the payoff, you win, minus the display is minus 10. Okay, so it's actually plus 15. So this is the actual payoff matrix for a hawk, a mixed ESS for hawk versus dove. This game is also called chicken. Like two people in fast cars that are racing head-on towards each other. It's to gain, let's say, status, or to gain death. It depends on your the way you're actually looking at life at that period of time. But you know, in the old days, well, probably nowadays too, perhaps guys are taking risky behavior. Actually, women are doing the same thing now. So whoever it is displaying to get, let's say, access to the other, to possible sex, right? Something like that.